Hello everyone and welcome to lab 3 of the course. In this lab we're going to design a quarter wave transformer and a single stub matching using microstrip lines. We're going to design these structures on ADS and HFSS and then compare the results we get from the two programs. Throughout the lab we're going to implement these designs using microstrip lines on Rogers RO4350 substrate, which has the following properties. And the traces of the microstrip line will be made of copper, which has this conductivity and this thickness. All right, so we'll get started with the quarter wave transformer. So as you guys know, a quarter wave transformer is a transmission line which has a length of a quarter wave, or lambda by 4 at the design frequency. And we can use it to match two real impedances such as Z1 and Z2. The characteristic impedance of that line is given by this equation, which is the square root of the product of the two real impedances that we want to match. Alright, so the question here is to design a quarter wave transformer to match two microstrip lines, which have characteristic impedances of 50 ohms and 150 ohms at a frequency of 2.xx, where xx are the last two digits of your student number. So each one of you guys will have a specific frequency, and this is what the final design would look like. So we're going to have the first microstrip line, 50 ohms. It's going to be matched to a generator, for example, so it's going to be also 50 ohms. The quarter wave transformer will go in between the first line and the second line, and the second line will also be matched to a certain load. Alright, so let's go through the questions. So the first question here is to calculate the characteristic impedance of the quarter wave transformer, and this can simply be calculated using this equation on 50 and 150 ohms. So you can go ahead and do that. 150 times 50, and then you take the square root. So that means the characteristic impedance of the quarter wave transformer has to be 86.6 ohms. So you can make a note of that. All right. Next question is to use ADS line calc tool to calculate the width of the three lines as well as the length of the quarter wave transformer. And as you guys may have already noticed, I didn't provide the length of the two other microstrip lines, L1 and L2, because their length doesn't really affect the design, so you can choose any reasonable length for that. So right now I'm going to go onto the server and we'll start ADS. So it's Advanced Design Systems, so you can search for that. And let's say we're familiar, create a new workspace. So we can call that lab 3, quarter wave transformer and stub. And you can put it on the H drive. If you go in here. And then create workspace. Alright, so we're going to use the schematic in ADS, so you can go ahead and create a new schematic. And the first one will be for the quarter wave transformer. Alright, so I'm going to assume that everyone can see the lab manual while I'm working on this. So I'm going to refer to the lab manual without going back and forth on the screen. Alright, so part B of section 2 is to use ADS line calc, and I tell you guys how to get there. So it's tools, line calc, and then start line calc. And this is an ADS calculator that allows you to either synthesize or analyze microstrip lines on top of substrates. So over here you will define the properties of the substrate and the metallization. Here you provide the frequency, and you can either provide a physical length and then analyze it to figure out what the Z naught is, or you can specify a Z naught and then synthesize to find out what the width of the line is. If you want to know the effective electrical length, you can analyze that, or if you want to synthesize a certain effective electrical length, you can synthesize it. We're going to be interested in the effective electrical length of the quarter wave transformer, but the other lines we can just specify a reasonable length for them. Some of the results that you will calculate as well are the effective relative permittivity, so that's K effective. So you can make a note of that as we go, because in the report I ask you guys to put a table for the effective permittivity for each of the microstrip lines. dB is the attenuation of the line in dB, and skin depth is the skin depth. Okay, so we can specify the substrate properties here. So from the lab manual, epsilon R of the substrate is 3.66. UR is just 1. The height of the substrate is 60 mel. The T here is the thickness of the metal, and it's provided as 0.001 millimeters. The conductivity of the metal is copper, which is 5.8 times 10 to 7. And then tan delta is the loss tangent, which is 0.004. All right, the frequency for the demo, I'm going to show for a frequency of 2 gigahertz, but you guys should do this for your frequency based on your student number. So your numbers will be different than mine. So I'm specifying 2. And let's say we want to synthesize the results in millimeters. So I'm just changing that here. So the first line is a 50 ohm line, so Z naught is 50. So if we synthesize that, you get the width of the line. So the width is 3.34 millimeters. So you can make a note of that. We're not interested in the electrical length, so you don't have to worry about it. And also see here the effective epsilon R is given here, so you can make a note of that for the report. All right, so that's for the first line. The second line is 150 ohms, so if you 150, and then synthesize, you get the width of the line, which is 0.229 millimeters. And finally, for the quarter wave transformer, the impedance is 86.6, and we want it to be a quarter wavelength, so the effective electrical length is going to be 90 degrees. So we can synthesize that. And here we get the width and the length of the quarter wave transformer. So the width is going to be actually 1.18, and the length is 22.9, and both are in millimeters. Okay. So this is all the information that we needed from line calc. And just a reminder, I did this at 2 gigahertz. So if your frequency is, let's say, 2.5, if you synthesize that, you will get different numbers. So make sure that you do it for your specific frequency when you're following along with the demo. Okay, so we can close line calc, and let's say don't save the changes. All right, so part B is done. Part C says on ADS, design and simulate the full circuit, including all 3 microstrip lines from 0.5 to 4 gigahertz, and show the results for S11 and S21 in dB. And finally, tune the length of the quarter wave transformer to achieve best matching at your design frequency. Okay, so let's go ahead and do that. So first thing we need to specify for microstrip lines is, of course, the substrate properties. So we need to add the M sub block, and we'll do that for millimeter. So we can add that over here. H is the height of the substrate, so you can specify that. It's 1.524 millimeter, given in the lab manual. Epsilon R is 3.66. mu r is 1. Conductivity is that of copper, which is 5.8. E to the 7. Metallic thickness is 0.001 millimeters, and tan delta is 0.004. Okay, and that's all we need for M sub. Next, we need to add the microstrip lines. So this is the M len block. So we need to add 1, 2, and 3 lines. The first line is the 50 ohm line, which has a width of 3.34. And the length here, again, doesn't matter what you choose, as long as it's a reasonable length. So you can say like 20 millimeters. The second line is going to be the quarter wave transformer, and that one has a width of 1.18 millimeters. Actually, for the width and length, I'm going to specify them as variables. So here I'm going to say W quarter wave transformer and length L quarter wave transformer. Made a mistake here. And I'm going to add a variable block for those variables. So if you double click here, first one is width of the quarter wave transformer. That will be 1.18. So you can apply that, and then length of the quarter wave transformer is 22.9. So you can add that. So let's say OK. And finally, the 150 ohm line has a width of 0.229, and let's give it the same length as the first line, so 20 millimeters. All right, now we can go ahead and connect those lines together. Perfect. Next, we need to add the terminations. So we want the lines to be matched on either side. So the termination to the first line will be 50 ohms. The termination to the second line will be 150 ohms. So you can go ahead and add the terminations. So you do term, add one termination here, one termination there. And we can also add the ground. Go ahead and add the ground here and here. Connect them together. All right, so this one is 50 ohms. That's good. This one we need to change it to 150. So 150 ohms. All right, looks good. Finally, we need to add the simulation block. So in our case, that would be an S parameter block. So you can search for S param, and you can go ahead and add that. So we want to have the simulation from, or the results from 0.5 to 4 gigs, and let's say 2001 points. Or let's do 3001 points, so it's really fine. Okay, good. So once you have all of that done, you can go ahead and simulate. Good, simulation is done, it's fairly quick. And finally, we need to show S11 and S21. So you can add a rectangular plot for S11 and S21 in dB. And there you go. So as you can see here, the reflection is at its minimum at the design frequency as expected. And the transmission is at its highest. And there's also a certain matched bandwidth. Usually we refer to the minus 10 dB matched bandwidth. So it's the bandwidth through which more than 90% of the power is transferred from one line to the other. So for example, here it would be from this point, from this frequency to this frequency. And of course, the best match should be at the design frequency. And if you put a minimum marker here, you can see it's almost exactly at 2. But just because we can, we will tune the length of the line in order to get it exactly at 2. Of course, in your case, it would be at your design frequency, like 2.5 or something like that. All right, so let's go ahead and tune the length of the quarter wave transformer. So we should go into the variable and make the length tunable. Should enable tuning here. Say OK, and then use the tuning fork, and we'll show the results so that we can see how it's changing. So it's probably a very minor change because it's already almost close to 2, so we can make the step really fine, 0.05. And since the frequency is lower than what I need to make the line slightly shorter. See, it's almost maybe even a finer step. Just there you go. So you can get it at exactly your design frequency, and that's what we want to see. All right, and once you're done with the tuning, you can save the tune values back to the schematics. Perfect, and that's the result that we need for part C. Part D is asking you to do the same thing on HFSS. So you guys have designed microstrip lines in the first 2 labs, so this should be a fairly straightforward task for you. And I'm going to show you what the design would look like. So this is what it would look like on HFSS. You're going to have the 50 ohm line, the quarter wave transformer, and then the 150 ohm line. And same thing as before in terms of wave ports and boundaries. The only difference is the microstrip lines now need to have a thickness, and you can do that either using, of course, a rectangular object, or you can create a sheet and then add a command to make this sheet thick. I'm going to show you that in the next section. Okay, so this part is done. You can go ahead and save the design. And just to note, in part E, I'm asking you to combine the S11 plot from here with HFSS. This one you can export. If you select the plot, you can export it to a text file, like a tab delimited ASCII text file, and which you can also read on MATLAB, just like the files you can get from HFSS. Okay, so close that and close that. All right, so this part is done. Now we can go on to the matching using a single stub. So I encourage you guys to read through the lab manual because there is a lot of information there explaining what we're trying to do. But the gist of it is, well, a quarter wave transformer can only match 2 real impedances. But the question comes up that what if you have a complex impedance that you're trying to match? So for example, if you have a certain complex load, RLC, that you're trying to match to a 50 ohm transmission line, how would you do that? And the idea is this complex impedance at a certain location along the line will have an input impedance that's equal to, that has a real part equal to 50 ohms and a complex part that could be anything. And at this location, what we can do is we can add a shunt element that could either be open or short-circuited in order to cancel out the imaginary part of the impedance. So the only thing left when you look at the shunt element plus the length of the line plus the load is simply Z0. So that's the idea of how this is done. Of course, this element is going to be in parallel with your load impedance and this line. So when we approach these problems, it's better for simplicity to express everything in terms of admittance. And the reason being that admittance in parallel add together. So if you're looking at Zn or Yn and you have a certain shunt admittance, all you need to do is provide an admittance of the same value and the opposite sign, and then they would simply cancel out when you add them together. So I provide the explanation here of what we're trying to do, so you can go ahead and read it. But we can start the problem and then I will explain it as we go along. Okay, so the question here is we want to design a single stub to match a complex impedance, which has R 100 ohms, L of 1.5 nanohenries, and C of 2 puff, to a microstrip line with a characteristic impedance of 50 ohms. And I'm asking you to design this at 2 gigahertz, so the design should be the same for everybody. All right, so let's start with the first question. Here I'm asking you to calculate the load impedance and admittance at 2 gigahertz. So I will let you guys do that because that's straightforward. I gave you the equation for the load impedance as well as the load admittance and the frequency that I want you to calculate it at, so that should be straightforward. Part B is asking you to calculate the normalized load impedance and admittance at 2 gigahertz. So if you guys remember, the reason why we do this is that we can plot these values on the Smith chart, and the normalization, of course, is done by either dividing the load impedance by Z naught or the load admittance by Y naught, and Y naught is 1 over Z naught. So again, this is a fairly straightforward thing to do. When you're watching the demo, I want you guys to actually do these calculations because in part C, we're going to or actually in part D, we're going to look at these values on the Smith chart. So I want you to be able to compare the values that you get from your calculation to the Smith chart. So you should go ahead and do these two parts. Okay, so part C is to use line calc to calculate the width of the line for a characteristic impedance of 50 ohms. So I have already done that from the last part, so I know what the width of the line is. It's 3.34. But if you haven't done it, if you've done it for a different frequency, you should redo it. So part C is to just calculate the width of the line over here for 50 ohm characteristic impedance. So that should be straightforward to do on ADS. Now the interesting part is part D, which is to design and simulate the load impedance and plot S11 on an impedance admin Smith chart and compare the results with the ones you got in part B. So let's go ahead and do that on ADS. So I'm going to go ahead and create a new schematic. I'm going to call that Stub. All right, so the question is to design and simulate the load impedance. So the load impedance has 3 components, R, L, and C. So we can go ahead and add those. So the first one is R, and if you want to rotate a component on the keyboard, you can just press Control R and that will rotate it. So first one is R, and then L, put that here, and then C, put that over there. All right, so R was 100 ohms, L was 1.5 nanohenries, and C was 2 puff. And then you can leave this R as 0. This is just the series resistance to the inductor, but we're assuming an ideal inductor in this case, so you can just leave it off from here. Okay, then we can add a ground here, and then we can connect them together. All right, so of course we want to look at this on the Smith chart, which means that we need to have a certain termination, and since our microstrip line is 50 ohms, or the characteristic impedance of the line that this load is connected to is 50 ohms, we're going to add a 50 ohm termination like we usually do. So you can go ahead and add that. Add a ground, and then connect them together. Last thing would be to add the S parameter simulation block to run the simulation. And here we're just interested in a single frequency point, so you can just say 2 and just 1 point. So it would run a single frequency point. Okay, so if you've done that, you can simulate. And we want to look at the S11 on the Smith chart, so you can click on the Smith chart here, and S11, and we want to look at it at S11 on an impedance / admittance Smith chart. So as you guys know, the Smith chart can show the impedance, and the reflection of that on the vertical axis is the admittance. So we can add both of them here, and there you go. So the gray part is the impedance, the red part is the admittance, and this point here is exactly what this load looks like on the Smith chart at 2 gigahertz. So you can make that full here. All right, so if you've calculated the load impedance and admittance from part B, which is the normalized 1 to 50 ohms, you should get a very similar result to what I'm going to show now. So this point here on the Smith chart is the impedance is Z0 times 0.227 plus J times 0.635. So of course Z0 is 50 ohms, so this is the normalized part, and if you multiply by 50, you would get the actual complex impedance. So you can go ahead and compare that with what you have, and hopefully these should be exactly the same. Now this is the impedance of this point. The admittance, you can read off the red part. You could actually also read the impedance of the gray part, but for some reason ADS doesn't display the admittance. If you figure out how to display the admittance here, you can let me know. But what we can do is we can zoom in here on this point, and then we can also read off the admittance of the load. So as you guys know from the Smith chart, this portion right here is the imaginary part, and over here this is the real part. So in this case, the admittance would be 0.5 plus J 1.4. So 0.5 plus J 1.4 should hopefully be close to what you've calculated as well. All right, so this is the load impedance on the Smith chart. The idea is we now want to move a certain distance away from this load so that it looks like the admittance is 1 plus a certain imaginary part. And again, the reason why we do this is so that we have our impedance Z0, which is going to be 1 when it's normalized, and we have an imaginary part that we can then cancel with the stub. All right, so I'm just gonna do a full screen here. So right now we need to move this around the Smith chart so that it lies on the 1 circle for the admittance. So you see the circle here. This is the 1 circle for the admittance. If you guys have done this in class in 3909, you would have had the impedance and then you would have transferred it to admittance, if you remember, because we only had the impedance Smith chart. But right now we have an impedance and an admittance, so we can simply just move this load, or move a certain distance away from the load, so that the input impedance is lying on the unity circle, and then the imaginary part we can cancel out with the stub. Okay, so that was a lot of talking, but we can actually go ahead and do that now with a microstrip line. Okay, so part D is done. So we've simulated the load impedance, and we've plotted the S1 on the Smith chart, and now you guys can compare the values, and hopefully they should be almost the same. Okay, so let's go ahead and save that. The next part is to add a microstrip line for D stub. So D stub is the certain distance away from the load, as shown in the picture in the lab manual. And I'm asking, what's the stub location such that yn1 is equal to 1 plus jb. So this is the same thing as saying, what's the location so that it lies on the unity circle for the admittance. Okay, so let's go ahead and add a microstrip line. So I'm just going to move that over here. And I'm going to add, but before the microstrip line, of course, I need to add the M sub for the substrate. So I'm just going to add that here. So it's the same thing as last time. So I'm just putting in the numbers. looks good for the M sub, and then we're going to add the M len. Add it here, and make sure you delete that line so that's not shorted. All right, so the width of the line is 3.34 for 50 ohms, and the length is the one that we're trying to adjust, right? So we can give that a variable, and then we'll add that variable so that we can tune it. So we'll go ahead and add that variable. If I double click on here, so this is the stub. We can leave the initial value as 1, and we're going to enable tuning because we're going to need that. Okay. Perfect. All right. So let's simulate that. And let's go ahead and tune. So if you guys remember, moving away from the load makes you rotate on the Smith chart clockwise. So away from the load towards the generator. So if I increase that to 40. If I make the step 1, as I increase the distance away from the load, as I move away from the load, the input impedance moves around in this fashion. So I can keep doing that, and the idea is we wanna be at a certain position such that the normalized admittance is 1. So we want to be lying on this circle. So I can keep going here, getting closer. Okay, we crossed over, so we'll just make the step slightly smaller. So go back. Okay, so at this point we are on the unity circle for admittance. So that's where we want to be, and the value to obtain that is 30.6 millimeters. So now we have that. The question is, at this location, what is the imaginary part of the admittance? So to know that, you just need to zoom in and see where the imaginary part is. So here it seems like it's just slightly more than -2. So the input admittance, which is yn1 from the lab manual, is 1 plus, or actually 1 minus j, and let's just say 2. 1 minus j 2. Question becomes, what value of shunt admittance do you need to achieve the other input impedance to be equal to simply 1? So what admittance would you need to add in parallel with this to cancel out the -2? And the answer is +2. Right? So if you put a shunt admittance, two shunt admittance together, they add. So if you have a -2 that you want to cancel, you simply add +2. And that +2, that's what we're going to get by adding the stub. So that's how this is done. Okay, so this answers the question for part E. So the value of the shunt admittance that you would need to cancel out the -2 is of course +2. Okay, so once you have that, you can just close the tuning, and you want to save the values back. Good. So let's close that. You can save the changes. Now the next part, part F, is to add another microstrip line for the short-circuited stub, which has a certain length, which we don't know yet, to achieve yn2 equals zn2 equal 1. So in simple words, what value of what length of stub do we need in order to bring that dot on the Smith chart to the center of the Smith chart? So that's what we're trying to answer now. Okay, so we can simply just add another microstrip line block, just a shunt in parallel, and we want it to be short-circuited, so we'll just add a ground for that. So you can just copy that here. Control R to rotate it, and then we can add a ground. I'll just move that up. Okay, so this one will be L stub, will be the length of the stub, and of course it would still be the same width because it's still 50 ohms. So we can go ahead and add another variable for that. So it'll be L stub, and we don't know what the value is yet, but for now let's choose one small value, and it will also still be tunable. Oh, it seems like it replaces, so I'm going to cancel that and just do that again. So once you do that, make sure you just add, so it creates another variable, and set that to 1. Okay, good. So we added a new variable for the length of the stub, and now let's go ahead and see what that looks like. Well, actually, let's ask ourselves a question. Based on this length, or actually let's choose a very small one. Let's say 0.5. So this is a very short transmission line, and it ends in a short circuit. What is the input impedance right now? If I simulate, what would be the input impedance on the Smith chart? So just think about that for a moment. Okay, let's go ahead and simulate. So if you've guessed that it would be very close to a short circuit, that would be correct, because we're simply just short circuiting the whole thing, right? So it would be a short circuit on the Smith chart as you would expect. And now the length of the stub, the job of the length of the stub is to provide a certain positive admittance to cancel out the negative admittance that we just talked about. So by increasing the length of the stub, we expect that we are going to get on the unity circle and eventually get to the center of the Smith chart, which is the goal of the whole design. Okay, so let's go ahead and do that. So we can pull up the tuner. And do that. Okay, so L stub is what we're trying to play with. So if I go ahead and increase that, you can see that we're rotating about the unity circle. And if you were looking at this without the rest of the circuit, so what I mean is if you were looking at just the shunt stub, this would simply move along the outside, of course, because if it's a short circuit and you're moving a certain location away from it, you would simply move along the outer boundary of the Smith chart. But of course, the combination of the load and the circuit makes it so that it approaches the unities, the center of the Smith chart. So if you slowly keep increasing, you'll approach the center of the Smith chart as expected. All right, so this seems to be very close to the center. Yeah, I would say this is good. So we need a 6.3 millimeter stub in order to match this this complex load. And of course, it's not just the 6.3 millimeter stub; it's also the location of the stub that's important. So these are the two parameters that we need. So I'm going to go ahead and close that. Say yes. Okay. That would be part F. So what is the length of the stub needed to achieve this? 6.3 millimeters. So that's what we need. Okay, so part F is done. Part G says implement the final circuit on HFSS, plot S1 on the Smith chart, and compare with ADS. Okay, so since you guys haven't done an impedance boundary before, which is basically implementing this on HFSS, I'm going to go through the design and show you how it's done. And then we'll also see that HFSS doesn't exactly match ADS, so we're going to have to do some optimization to get to the center of the Smith chart. Okay, so let's go ahead and do that on HFSS. All right, so I've already designed it, and so I'm going to show you what the final product looks like, and then we'll work on it together. So this is the whole design. So actually, before I go there, let's go back to ADS and let's ask a question here, because this is important. So right now, as you guys have seen, we are exactly in the center of the Smith chart, or close enough to the center of the Smith chart. Now, what would happen if I go ahead and add a transmission line here, or another microstrip line, which is 50 ohms? What do you expect to happen? Do you expect the position to change? Let's say if we were exactly in the center of the Smith chart. So if you answered no, that would be right, because once we have an input impedance of 50 ohms, if you add another 50 ohm line, that doesn't change it. It's still perfectly matched. And the reason we do this is in a real life situation, your stub wouldn't be at the edge of the board. Normally, you would want to have a certain transmission line so you can connect your coax cable or whatnot. So if I add another microstrip line here, I should not affect the result, and I'm going to show that now. So if I just copy that, put it here, and again, just make sure you delete that line. And this length doesn't matter. I can just say 20 millimeters. This length is important because it's the location of the stub. This one, not so important. Okay, so hopefully we stay in the center, and we're pretty much still in the center. So this proves that once you're matched by the stub, your results should not be affected. Good. So that's what I wanted to show here, because I did use it on HFSS, and I wanted to implement the exact design that you guys see here. One other thing is, let's say once you've designed this, and when you go into the report, I ask you about the Smith charts and intermediate steps. You don't have to redo everything from scratch. What you can do is you can simply short circuit and open circuit components as you need to. So for example, if I want to go into the result from part D, which I only had this, I can just select these two and make them short, and then select this one and just make it open. And then if I look at that, I should just see the result that we initially had, if you guys remember, from part D. And then for part E, I can just activate that again, so that I'm looking at the result where it's at the unity circle. And then for the last part, you can also just activate that. So now we're looking at the center. Just something you need to know, so you don't have to redesign things from scratch. Okay, now with that in mind, I'm just gonna activate that again. Now with that in mind, let's implement this circuit on HFSS. And as I just showed you guys, this would be the final design. So the blue here is the length of the stub, or the D-stub parameter. This is the stub, which is short-circuited here, and this is the length of the transmission line, which its length should not matter. This is a wave port over there, and this small little thing there is our load, which we define in HFSS. So instead of just showing you guys, I'm going to go ahead and do it from scratch, so that we can see how it's all done. Okay, so I'm going to create a new design here. Okay, so you guys are pros at this now, so I'm just going to go ahead and build the stuff that we need to do. So first thing would be the substrate. It would be a rectangle. And I've already used it in this project, so it's predefined here, but you can always go and search for it. It's Rogers 4350. And the substrate. And I'm gonna make it slightly transparent, so we can see the short circuit for the stub, which I will show in a little bit. Let's say the width of the stub is like 3 centimeters. Now the length of the stub would depend on the length of the two microstrip lines, but for now we can just give it a number, and we'll go back and fix it later on. Just say 5 centimeters for now. And the height is sub h, and that is, hold on, sub h, and that's 60 mils. Okay, so that's the substrate. Let's go ahead and create the lines. So for the microstrip lines, because now they actually have a thickness, you have two options. You can either draw a box with that thickness, or you can draw a surface and then give it the thickness. So I'm gonna go with that option. So I'm gonna put a surface on. So that would be the first microstrip line. Call that MS1. color. Say MSW 2, 0, and sub H. And the width of the line is 3.34 millimeters. The dimension in X would be MSW. And in Y, it would be the length of the line in ADS that we added at the end. I think that was 20. I think it was 20 millimeters, if I remember correctly. Yeah, so it's this line right here that we're trying to design. Okay, so 20 millimeters. Good. So again, right now it's just a sheet, right? And the sheet has 0 thickness, but we can actually give it a thickness if you right click, edit, surface, and then thicken sheet. Right now we just want to thicken it in one direction, which would be the positive Z. So you can leave this unchecked, and the thickness, wonder if we can create a variable here. Yeah, we can create a variable T, 0.001 millimeters. And right now it became an object, as you would have expected. And we want this object to be copper. Good. So right now we're exactly the same as ADS. All right, so that's the first line. The second line is the one which is important in its length because it determines the location of the stub. So you can go ahead and copy that line and simply just change the dimensions so that it starts at MSL and its length would be dstub. I'm just going to keep using the same variable names. And from ADS, dstub was 30.6. So 30.6 millimeters. 30.6 millimeters. Okay, and it would have the same width, of course. So now you can see it's extending a little bit over the substrate. So we can go ahead and fix the substrate length so that it's corresponding to the sum of the two lengths of the lines. So it's going to be MSL plus dstub. Should be exactly good. Okay. And I'm gonna give that line a different color so that you can see where everything is. Okay. Now finally we need to add the stub. So the stub would be another microstrip line, and it's going to extend after here. It's going to go in either up or down, and it's going to be short-circuited at the end. I'm going to go up with that. So in terms of the X dimension, it's going to be over there. That would be correct. In Y, it would start there as well. The X size, however, will be the length of the stub. So it would be L stub. We can create a new variable for that. From ADS, this was 6.3. So we can go ahead and say 6.3 millimeters. And actually, no, we want it to be, in X, we want it to be minus L stub. So it goes up. And the Y size would be, well, it's going to be the width of the line. And since we want it to go in the negative Y, it's going to be minus MSW. And there you go. That'll be the stub. And I'm also going to give it a different color, so we can distinguish it from everything else that's going on. So 3 microstrip lines, all of them made of copper and have a thickness of T, 0.001. Okay, so far so good. Next we can go ahead and just add the radiation box. So I'm just gonna put the box somewhere. It's gonna have the same dimensions as the substrate in the XY plane. Let's say we'll give it 15 times the substrate height in the Z direction. Okay, I'm gonna make that more transparent so you can see what's going on inside. Good, radiation box is defined, and let's go ahead and define the boundary while we're at it. So if you select this face, this face, and then this face and this face. So all the 5 faces except the bottom. So you can assign that as a radiation boundary. Good. Just making sure here that it got assigned. Perfect. Okay, so now there are 3 things left. We need to put in the wave port. We need to make sure that this stub is actually shorted to the bottom of the substrate. And we need to add the load impedance. So let's go ahead and add the load impedance, because that's an important one. So we just need to add a surface for that, or a sheet. And we want to add it in the XZ plane. So XZ. So again, as usual, just put it somewhere, and then we'll make sure that it's right at the edge there. So this one will be our load. Just go ahead and define that. So the location here would be the width of the line. It's going to be at the end of the substrate, and say it starts at 0. Of course, this will be MSW, and this will be sub H. All right, so that's where it is. We're at the end here, and we'll give it a color that's can be easily distinguished. So that's good. So that dark blue is our sheet that will be the load. So once you have that created, you can right click, assign boundary, and then lumped RLC. So that's what you want to assign. And you want the components to be in parallel, of course. So you want all of them, because we have a resistance, which is 100. We have an inductance, which is 1.5, and a capacitance, which is 2. And then you also need to define the current flow line. So that's just simply the direction of the current flow. So you can go ahead and so you can zoom in here. So if you just select, say from here to the bottom. Okay, it says it's invalid. Let's see, the boundary, the endpoints must lie on the boundary face. Okay, so it seems like we started somewhere not on the boundary face. Okay, so what I'm going to do is, before I'm going to say new line, I'm just going to hide the number of things. I'm going to hide this line. Okay. All right, let's cancel that. So this is the load. I'm going to show that. I'm just going to hide this line, so that we can only select things on the face of the load. So if you go ahead and do the same thing, assign boundary, RLC, and parallel, resistance, inductance, capacitance, 1.5 and 2. And let's give that another shot. So the current is going to flow from there to there. There we go. All right. So that's good. So lamp RLC, you can just leave it as that name. Let's show everything again. All right, so now we assigned our boundary for the load. Next, we need to put a sheet that will short circuit this stub. So we can go ahead and create a sheet in the YZ plane. So it's going to be a sheet in this plane. So this one will be our, let's call it stub short. Okay. And also give it a color that we can see. All right, so in terms of the location of that, it would be maybe start here, end there, and then go down. Okay, let's see if we can do that. So position in X would be minus ms w over 2 minus L stub, right? Would be the position in X. position in Y would be it would be MSL, be the length of the line, and then in Z let's start at 0. All right, the size in Y would just be minus MSW, and then the size in Z, of course, would be the sub H. Good. So it's right there, and then you can see that it's going down to touch the ground of the substrate. All right. Once we have that created, we can of course assign it as a copper boundary. So go ahead and say that's copper. Okay. Now the only thing left is the wave port. So you guys have done this a few times now. So create a variable for that. 0 and 0. And it's going to be 6 times the width of the line. Good. And here, that, and of course the height will be 6 times the height of the substrate. Good. Okay, so that should be good to go. We've assigned all the boundaries that we need to assign. We did not assign the wave port excitation, so let's go ahead and do that. And one other thing that we can do, which will be useful later on, is to actually de-embed the wave port so that we can look at the impedance right after the stub, because we want to make sure that this impedance is 50 ohms, because if it's not, this line will cause a problem. So what we can do is we can take a top view here. We can de-embed the wave port into this location right here. So this is equivalent to YN2 or ZN2 on the lab manual. All right, so we can go ahead and do that. So if you go and de-embed, so the de-embedding here would be the length of this line minus the width of that line. So the MSL minus MSW. There you go. So we're just so that we're viewing all the results at this point. Okay, that looks good. Now we just need to add the analysis, and we can leave that as 5 gigs. Number of passes, let's say 15, 0.01. Minimum number of passes is 6. Minimum converge is 3. And we're only interested in of course 1.2 gigahertz, so we can do a discrete so we can get the maximum accuracy, and we can do a single point 2, and we're not interested in the field results, we just want to look at the Smith chart, so you can just leave that unchecked. All right, let's see here. Validate. So there is a warning that the radiation boundary and the lumped element RLC overlap. So as long as you defined the RLC boundary after the radiation, I think you should be okay, because that means the RLC will take precedence. So this warning should be okay. All right, so if you have everything done, we can go ahead and analyze. All right, so just think about this. Do you expect the results from HFSS to match exactly with ADS? And if not, think about why. And if not, what can we change to make them match? And while you're thinking, let's watch the conversions. Yeah, seems like it's converged. Good. All right, so we want to look at the S11 on the Smith chart. So let's go ahead and Smith chart, S11, sweep. So the frequency is going to be at 2. Perfect. And let's see what that looks like. Okay, so what you would have expected based on ADS is that this would be right in the center of the Smith chart, but you didn't get that. And that is something I want you guys to think about. Why do you think the results from HFSS and ADS don't match exactly like you expected? And this will be one of the things that you will also need to discuss in the report. And of course, you can ask me during the lab, and I will give some hints. But think about it, why it's not matching. And now that it's not matching, what can we do to fix it? So ADS has the tuner capability, which allows you to change the variables and view the results almost immediately. But that's because the results in ADS are fairly quick. But in HFSS, you don't really have a tuner. You either do a sweep or you can do an optimization. And that's what we'll try to do now. So we want an optimization, or we want to run an optimization routine to bring this impedance right in the center of the Smith chart. So S11, we want it to be as close to the center of the Smith chart as we can. And so S11 on the Smith chart, if it's in the center of the Smith chart exactly, in dB, that corresponds to a very low negative number. So something like minus 200 dB. But of course, we don't want to give HFSS something that small to work with. So what we can do is we can run an optimization to have S11 less than minus 30, and that should get us pretty close to the center of the Smith chart. The next question is, what are we running the optimization on? So the only things that affect this is, of course, the length of the stub and the location of the stub. So the two parameters that we're going to need to optimize are D sub and L sub. So let's go ahead and do that. So before running an optimization, you have to select the variables that you want to optimize. So if you double click in the variables window here and go on optimization, you can select D sub and L sub to be included in any optimization that we want to run. You can also specify the minimum and the maximum values for the optimization. And that's probably a good idea to do. Don't just go with the values HFSS gives you, because you want things to be reasonable. I mean, ADS and HFSS are trying to do the same thing, so the differences should not be that huge. So for example, if D stub from ADS is 30.6, you expect ADS to be, or from ADS it's 30.6, you expect HFSS to be plus or minus a couple of millimeters. So for example, I hear total guess, by the way, I don't know what the final value is. You can specify something like 27 for the minimum, and the maximum is 33. And of course, if that doesn't work, you can come back and change it. But normally you don't want to give the optimizer a huge range to work with, because that means it would take longer to get to the value that you want. And I don't know if this optimization will finish before the end of the video, or I might have to just cut it short and say this is acceptable. And of course, I don't expect you guys to run a simulation for 10 hours to get the exact result, but I think this will converge fairly fast, as you will see. Now for L sub, again, it's 6 millimeters, so let's say from 3 to 9, something reasonable like that. Okay, so once you have those specified, you can say okay. Now you can go on and add the optimization. So right click on Optometrics, add optimization. And if you go on variables, you will see the variables that we just included are here. The goal, the optimizer type, I don't know the exact difference between all of them, but in my experience, the pattern search seems to get to the result the fastest. But again, that could be different for different designs. Maximum number of iterations, of course, that makes sense. You have to specify a maximum number of simulations before it has to stop. And just for the sake of time, let's say we don't want more than 15 simulations. And I definitely don't want you guys to run 1,000 simulations on the server, because that could take a very long time. So let's say we'll just set it maximum at 15 for now. Now, the most important thing in optimization, of course, is the cost function. So you want to tell HFSS what kind of solution that you want to get. And for us, that is simply just an S11, and let's say in dB, and we want that to be less than minus 30. So less than minus 30 is not exactly in the center of the Smith chart, but it's very, very close to the center. And of course, minus 30 is very, very low reflection already, so that should be good. So we want it to be less than minus 30. Okay, so once you have specified everything here, you can say okay. And just run the optimization. And of course, as we always do, we always define everything in terms of variables, and this allows the optimization to work correctly because we defined the length of the line as a variable, and we also defined the substrate length as a variable in terms of the line length. So that means whenever the line is changing, the substrate is going to change with it. So that shows you an even more reasons to use variables when you're designing things like that. Okay, so while it's going, we can actually watch on the Smith chart what's going on. So if you go on here, if you go under families, it's not showing yet because it's only one. You can see, we'll wait until this is done, so it's solving a couple of them, and then we'll go and try to view all the results in the same window. Okay, while this is running, I'm just going to go through the lab manual and see if there's anything else that I want to mention. So what we're doing, by the way, is part H. So it's optimizing the stub location and length to achieve S11 less than minus 30. And the question is, what are the new values of these stub and L stub? And that's what we're going to find now. Okay, so the report guidelines are fairly similar to the previous lab, except that now I want you guys to submit the ADS files. So for that, you simply just compress the ADS project. So if you go into your H drive to where you saved your design. So for me, it's that one. So you just compress that folder and include it with the report. What else? So the Smith charts, you can, of course, you're not gonna export, but other data like which is actually pretty much just for the core wave transformer. I want that to be exported and plotted on MATLAB, and on the same plot show ADS and HFSS for a better comparison. Okay, I think that's pretty much it. I think the biggest part of the lab and what I really want you guys to think about is try to understand the difference between ADS and HFSS, and you can do a little bit of research on your own, and that's why there's 5 marks on the discussion, because I want you to go in a fairly good detail comparison between the two programs, and at the end, which one would you trust more? Let's say if you had all the computer resources, of course you can see HFSS takes a lot longer to run than ADS, but let's say if you had all the resources, which one would you rather use if you had the resources and time? Okay, so it seems like it already solved 4. So let's go ahead and look at all the variables. So select all and all, and create new report. So here you can see. I think we started somewhere around. So we started at this point. We started here. So HFSS is trying to see which point will get us to the center. And remember, we only give it a maximum of 15 iterations. So let's see if it gets to the center within 15. So you can just sit back and watch. Remember, it's not trying to it's trying to get to the center by looking at the S11 in dB. So you can also plot S11 in dB and see what that looks like. So I guess you'll have to. Okay, let's look at that dB. Yeah. All right, so you can see here the best it has achieved so far is minus minus 12. So there's a little ways to go to minus 30. All right, you can see it's getting a bit closer, and with that that variation here. So if you look at that here on the Smith chart, that's below minus 15. And I mean, for all practical purposes, minus 15 is a very good match. Like if something has a reflection coefficient of minus 15, you can do the calculation, but it's probably less than 5% reflected power, and usually the industry standard is minus 90%, so around minus 10 dB. So minus 15 is still fairly good. But let's give HFSS some time to try and get to the center. And of course, I mean, there is a variation to get to the center. It's just might take a bit longer than ADS. And just so that people don't try to optimize until they get to the center, let's just say that you only run an optimization for 15 iterations, and that's it. And the best value you get, that's the one that I want to see in the report. So that should make it easy. So you just run this once, 15 iterations, and then whatever point that the best point that HFSS can get, this is what I want you to show in the report. And then of course the expectation is that the discussion will be detailed, and this is expected either way. I mean, I already see that it's probably gonna get to the center. We have 5 to go, so it's getting there. So on the Smith chart, it's already at close to minus 20. getting closer. Let's look at the, so now it's at minus 20. So again, just a reminder, just run it for 15 iterations and that's it. Whatever the best value that HFSS arrives at, that's the one that I want you to show in the report. All right, so it finished the analysis, and well, the best it could do was minus 20, and that's okay. So if you look here, so this is the closest it could get it in 15 iterations, and that's okay. So once you do that, this is what you can show in the report, and HFSS will automatically update the variables with the new numbers. So over here, D stub is 28.3 and L stub is 8.3. So slightly different from ADS, a few millimeters variation as I expected. So now, question is, why is that the case, and what's different from here to ADS that would cause this difference? Okay, so in terms of the plot from here, all we need is the plot of the optimized S11 and the new variables and the new dimensions of D stub and L stub. So I think this is the end of the demo, and I will see you guys in the lab.